Well, let's take a look at section 2.2 that's talking about quadratic functions. So first up here, let's talk about what we need to be able to do by the end of this section. We'll be able to recognize characteristics of parabolas, be able to graph the parabolas, and determine the quadratic function's minimum or maximum value depending upon whether the parabola is pointing up or down. And then we'll be able to solve problems involving quadratic functions maximum or minimum values. So application problems that are basis of quadratic functions. Okay, first up here. We know that the standard form of a quadratic function is the following. We saw this back whenever we were shifting and reflecting functions. Let's say I have a quadratic function. F of x is equal to a times the group x minus h quantity squared plus k, where a is some number other than 0. So in other words, you have to have an x squared term. Well, all this means here in this case, based upon what we've already talked about with the shifting and reflecting and stretching and all that stuff, is that x is being shifted, or I should say y equals x squared, the parabola that normally starts at 0, 0, it's been shifted h units to the right and k units up, and then it's stretched by a factor of a. Now, it's going to get larger if a is a number larger than 1, and I shouldn't say stretched, but shrunk if a is a number between 0 and 1. Now, as far as what we're talking about in this section, we just said, well, this is the standard form. And we need to understand that the vertex, because it's being shifted h units to the right and k units up, the vertex is the point, the ordered pair hk. The parabola is going to be symmetric about the line. If you could draw a vertical line that goes right through the vertex of that parabola, of course it's going to be symmetric with that. So it's just x is equal to whatever the x component of the vertex is. It's going to be symmetric about that vertical line. Now, we know that parabolas are going to open upward anytime the x squared term is positive. So if a, the coefficient of the x squared term, is positive, it's going to open up. If it's a negative parabola, if a is less than 0, then the parabola is going to open down. Now, when we look at this standard form equation, whenever we're trying to graph it, the first thing that we're going to do is that process of realizing whether it opens up or down, and that's easy. If the x squared term is positive, it opens up. If the x squared term is negative, it opens down. We'll determine the vertex of the parabola by just looking at the equation and figuring out what h and k are. Please do keep in mind that it's always the opposite of whatever is in with the x. So if you see x plus 5, well, then negative 5 is the x component of the vertex. Up next, we'll find any x-intercepts, and you know that the x-intercepts always occur when y is 0. So you just set your function equal to 0, solve for x, and those are going to be your x-intercepts. Now, we know not all functions have x-intercepts. If you have a negative discriminant, if the term underneath the square root's a negative value, then you know it's not going to cross the x-axis. But whenever you have a positive number under the discriminant, absolutely you're going to have two x-intercepts. If you have a 0 as your discriminant, then you're only going to have one x-intercept. It's going to touch and go back in the direction it came from. Now, up next, we're going to find the y-intercept by computing the function's value when x is 0, so f of 0. And then you're going to plot these points we just found. So you plot the x-intercepts, the y-intercepts, the vertex, and then just connect these with a smooth curve. And I say any additional points, but usually we don't need any additional points. Connect these points on a smooth curve, and it should be shaped like a bowl or an inverted bowl, depending upon whether it's going up or down. Let's take a look at one of these. So let's say I give you the example where I'm asking you to graph the function, and this is in standard form, -1 times the group x minus 1 quantity squared plus 4. All right, first part's easy. Determine how the parabola opens. Well, of course it opens down because you have a negative multiplying the x squared term. So we already know since a is a -1, which is less than 0, it's going to be pointing downward. Now, What is the vertex? Well, we know the vertex is always the opposite of this number. The x component is going to be positive 1. The y component will be 4. Our vertex is going to be the ordered pair 1, 4. Now, after you determine the direction it opens and the vertex, the next thing is to find its x-intercept. So you say, well, set the function equal to 0. Here's my function. I set the function equal to 0. Now I solve for x. So I get the group that x is a part of by itself. I'll subtract 4 on each side. Then I divide by negative 1 on each side, and I get the group x minus 1 squared is equal to 4. Well, now when I take the square root of both sides, I'll get x minus 1 is both the positive and negative square root of 4, which is plus and minus 2. Now that gives me two simplistic linear equations to solve. I have x minus 1 is 2. I add 1 to both sides and get x is 3. Then I have x minus 1 is negative 2. I add 1 to both sides and I get negative 1. So these are my two x-intercepts. You could list them as x equals 3 and x equals negative 1. It's probably a little bit superior to go ahead and list out the ordered pairs. You know, if x equals 3 is your x-intercept, it's the ordered pair 3, 0. And then we have our other x-intercept at the ordered pair negative 1, 0. The y value is always 0 when it's crossing the x-axis. Now we need to find where it's crossing the y-axis. And you just say, well, it's crossing the y-axis when x is 0. So you literally just plug a 0 in for your x value. Notice here, that's going to give me 0 minus 1. Well, that's a negative 1 squared, which we know is 1. But then you have a negative out in front of that group. So we're going to have negative 1 plus 4. We're going to get a y-intercept at y equals 3 for a coordinate point of 0, 3. Now, I need to take these points that I just found, the y-intercept at 0, 3, the x-intercepts at negative 1, 0, and 3, 0, and my vertex, which I found to be at 1, 4. I take those points, draw out a smooth curve. I don't ever need you to plot any other points other than those. You're certainly welcome to if you wanted to. For example, I know the ordered pair 2, 3 would be a point on the curve because as you move from the vertex, it has to be symmetric. So if I move 1 to the left and go down 1, then I would move 1 to the right and go down 1. I know the ordered pair 2, 3 would be a point. No need to put any other points on there, though. This is fine. Okay, up next, what if your original problem is not in the standard form, but it's in general form of a quadratic? So if you're given f of x is equal to ax squared plus bx plus c, you could complete the square on that and get the standard form and work the problem like we just did the previous one. But the quicker way is to just go in and say, well, anytime it's in this format, then the x value of the vertex every single solitary time is the coefficient of the x term divided by 2 times, I should say the negative of the coefficient of the x term divided by 2a. So if it's ax squared plus bx plus c, the x value of the vertex is at negative b over 2a. Now, once you find the x value of the vertex, we know the y value, it's just your function's value at that specific x value. So we can plug in f of negative b over 2a, and it comes out pretty easily. So now, if I were graphing functions that are given to us in general form, ax squared plus bx plus c, your first step stays the same. You have to decide whether it's going to be pointing up or pointing down, and that's a very easy choice. If the x squared term is positive, it points up. If the x squared term is negative because a is less than 0, it's going to point down. Determine the vertex of the parabola. No problem, we just talked about that. The x value of the vertex will always be at negative b divided by 2a, and the y value is just when you plug that answer for negative b over 2a into your function. After you do those 2 steps, again, the remaining steps, pretty similar. How are we going to find our x-intercepts? Every single solitary time, you find them by setting y equal to 0, or in this case, f of x equal to 0. So you set the y value to 0, solve for x. Those are your x-intercepts. Similarly, you find the y-intercept by setting the x value equal to 0. So you'll just plug in 0 into your function, and that's going to equal c, where that c value is your y-intercept. And then the last step, you can plot these points, the y-intercept, the x-intercept, and the vertex, and you'll have a smooth graph of your parabola. Now, let's go ahead and look at that. So graphing a quadratic function, and when I said parabola, a graph of a quadratic function is called a parabola. So if I graph the quadratic function, negative x squared plus 4x plus 1. So similar to my last example, I see that the x squared term is negative. Clearly, step 1 then, I know it's pointing downward. Step 2, find the vertex. It's not as obvious as the case where it's in standard form, but it's certainly not hard. You just say, well, the x value of the vertex is always going to be at negative b, which is going to be at negative 4, divided by 2 times a, which is going to be 2 times negative 1. Please notice that's what I did here. Negative 4 over 2 times negative 1. That gives me a negative 4 divided by a negative 2, which is a positive 2. So now I know that my x component of the vertex has to be a positive 2. The y component is just going to be when I plug a 2 into that equation. So finding the vertex, I'm still doing step 2 on the next page. You'll see, what do? I need to find the y value. I plug x equals 2 into your equation. It was negative x squared plus 4x plus 1 becomes negative 2 squared plus 4 times 2 plus 1. When I plug that in, I get a y value of 5. So now I know that the coordinates of the vertex are the ordered pair 2, 5. All right, so I have my vertex. I have the fact that it's pointing downward. What's next? The x-intercepts. To find the x-intercepts, you just set the equation equal to 0. Now, probably the easiest way to do that is the quadratic formula, so you're welcome to do that. If you wanted to be cool and use completing the square, that would be awesome, but quadratic formula is probably the easiest. Here you'll see I did the negative b plus or minus the square root of b squared minus 4ac all over 2a. And when I plugged the values in here, the b was negative 4 plus or minus the square root of b squared, 4 squared, minus 4 times a, which is a negative 1, times c, which is a 1, all over 2 times a, 2 times negative 1. The inside, the discriminant portion simplified to be 16 plus 4, which we know is 20. And now please, please don't leave your answer like that. That needs to be simplified. That square root of 20 has a perfect square factor of 4. I could break it into the square root of 4 times the square root of 5. And oh goodness, I didn't do that in this case because in a graphing problem, we want a decimal answer anyway, which is wimpy. So that's the only reason I didn't do that in this case, is because I was just intent on graphing. If I wanted an exact answer, I would want you to break that square root of 20 down. So keep in mind, the only reason I did not do that in this problem is because I was trying to graph it. So instead of getting that square root answer, I wanted a decimal answer to make it easier to graph. This first fraction gave me a negative 0.2 approximately, so that's one x-intercept. The other x-intercept was approximately positive 4.2. So my ordered pairs were negative 0.2, 0, and 4.2, 0. Now, for the next step here, the y-intercept, you just say, well, plug a 0 for x into your equation, which was negative x squared plus 4x plus 1. Notice that's negative 0 squared plus 4 times 0 plus 1. Well, clearly, when you plug a 0 into that, the x terms cancel out, and you're just left with that 1. So the y-intercept is just the constant in your quadratic formula equation, and it's going to be the 1. Our y-intercept is the ordered pair 0, 1. Now we have everything that we needed to graph. We have our x-intercepts that we found using the quadratic formula. We have the y-intercept we found by plugging in a 0. The vertex we found by using negative b over 2a and f of negative b over 2a. And the axis of symmetry is just a vertical line going through the x component of your vertex. I'm really not crazy about you plotting out the axis of symmetry. You can, though. So now when I plot this function, I can say, well, the vertex is at the ordered pair 2, 5. I got that point in there. Y-intercept at 0, 1. My x-intercept's at -0.2 and at 4.2. And then if you wanted to draw a vertical line through to the center of this to show the symmetry, you can. But please remember, the axis of symmetry is an imaginary line that's not part of the graph of the parabola. It's just used to show the symmetry of the parabola. And then as far as I'm concerned, you could connect these points in and be done with your problem. Gorgeousness. Now, whenever we're thinking about application problems are going to be mainly concerned with maximizing or minimizing some event that is going on. So we need to remember, whenever the x squared term of a parabola is positive, that means that your function is going to be pointing upwards. So that's what I'm saying here. If a is greater than 0, then your vertex is going to be a low point, and that y value there is going to be the minimum. So I say the minimum would occur at -b/2a, and the minimum would be the function's value at -b/2a. Well, what if a is a negative value? What if you have a negative quadratic? Well, if it's negative, then your function is going to be pointing downward and your vertex is going to be a high point. So you can say, well, then the maximum is going to occur at the x component of that high point, and the y value will actually give you that maximum value. So now, that's what I was trying to say on the last page. In each case, the value of x gives the location of the minimum or maximum, and the value of y gives you the actual value of the minimum or maximum. Now, to see that in action, let's say we're looking at the quadratic function 4x squared minus 16x plus 1,000. I want to determine without graphing whether the function has a minimum or maximum value. Well, that's super simple, because I can look at it and say, well, it's a positive 4x squared. Every single solitary time the coefficient of x squared is positive, your function points up, which means it has a minimum. So I can say, since a is a positive value, which is greater than 0, the function has a minimum value. Now, what is this minimum value? I go in and I can say, well, in this problem, a is 4, b is -16, and c is 1,000. The x component of that minimum vertex is going to be at -b/2a, which gives me the negative of -16 over 2 times 4. That's going to be positive 16 over 8. I get an x value of the vertex of 2. Now, that's only when the minimum occurs, not what the minimum is. So in order to find the actual minimum value, now I have to plug 2 back inside my function. So I can say, well, f of 2 is going to give me 4 times 2 squared minus 16 times 2 plus 1,000. See, that's what I did here. That's going to be 4 times 4 minus 32. So 16 minus 32 plus 1,000. It's a -16 plus 1,000 for 984. Now, keep in mind, that's a minimum value because this was a positive parabola. So we can say that the lowest value this parabola ever takes on is a value of 984, and then it's going to go up. So the minimum occurs at x equals 2 and at y equals 984. So the minimum value of 984 occurs when x is 2, and then it's just going to go up as x moves to the left or right of 2. Now, whenever we're thinking about that, a lot of your homework problems will be asking you the domain and range. Please remember, the domain of any polynomial function in existence, and a quadratic function is certainly just a subset of polynomial functions, their domain is always -infinity to infinity. You can't plug any x value into this quadratic equation and make it undefined. It's not going to happen. So for all real numbers, it's defined. So the domain, it's going to go all the way to the left, all the way to the right, -infinity to infinity. But now, the fact that we found that that vertex was at 2 and 984 shows us that the lowest the y component could ever get is 984. And then it's only going to go up. So we know The range, the y values, it's going to start at 984, and it will include that point because that point is the vertex, but then it's only going to go up from there, so the range is from 984 to infinity. Now, when we're looking at solving problems involving maximizing or minimizing quadratic functions, the first step in order to do that is, of course, you need to read the problem carefully to understand whether you're trying to maximize or minimize the relation going on in your application problem. You certainly don't want to maximize if you're supposed to minimize, or vice versa. Use the conditions of the problem to express the quantity as a function of one variable. That's a problem I see all too often with students is they'll get their equation in terms of two variables and say, well, what do I do with this? Well, the quick answer is you don't do anything with the two variables. You've got to get it down to one. Then last step here is to rewrite the function in the format of, or actually it's the third step, not the last step. There's two more. Rewrite the function in the format of f of x equals ax squared plus bx plus c. Typically that quadratic form will be easier to work with application problems. And then after that, you know that the maximum or minimum value is going to occur when the x value is negative b over 2a. And then the actual value that's the maximum or minimum will be the function's value at that point. And then, of course, we'll answer the question posed in the problem. Let's see an example of that. So in this case, I'm looking at an example, and you'll have homework problems like this. It says you have 120 feet of fencing to enclose a rectangular region. We're supposed to find the dimensions of the rectangle that maximize the enclosed area. And then what is the maximum area? All right, so we know that we're looking to maximize. That's clear. It says in the problem, what is the maximum area? So step one, super easy here. We're looking to maximize area of a rectangle. Step two, express the quantity as a function in one variable. So first off, you just might say, well, area of a rectangle is length times width. Or in terms of variables, we normally call the horizontal component x and the vertical component y. So I can say, well, area of a rectangle is x times y. But that's not too helpful in and of itself because I need it in terms of one variable. So what I do is I use the information given in the problem and say, well, yes, I need to maximize that area function of x times y, but I know I have 120 feet of fencing. So the perimeter around the entire object would be 120 feet. So that would mean 2 times the width plus 2 times the height, 2x plus 2y has to be 120. That allows me to solve that equation for y in terms of x. So I can say, well, then 2y is going to equal 120 minus 2x. Now I divide by 2, and I can say, well, 2 is going to distribute into this group and give me 60 minus x. So now I know that if I allow x to be the amount of the width of the fence, then the height of the fence has to be 60 minus x. So now I can go over to my area formula. Width times length is going to be x times y turns to x times 60 minus x. I distribute this x through the group and get 60x minus x squared. It's probably better to write that in quadratic form with a descending order. So I said, well, negative x squared plus 60x. Now, this is in the format of ax squared plus bx plus c. I have negative x squared plus 60x. Clearly, I know that I will be finding a maximum because this is a negative quadratic. The vertex is going to be a high point. So I calculate where that high point occurs. And I say, well, the x value of the vertex is going to be at negative b over 2a. That's going to be negative 60 over 2 times negative 1. That's negative 60 over negative 2 gives me positive 30. So I know that the maximum area occurs when x is 30, and then you could quickly see, oh, well, the y component is going to be 60 minus 30. It's going to be 30 as well. The area is going to occur whenever the dimensions of the width and length of this rectangle actually make it a square. They have to be the same in order for the area to be maximized. But going ahead and making sure we follow through with the formula, I can say, well, since a is less than 0, we know that the maximum is going to occur when x is 30. So if I plug 30 into my area function, it will give me my maximum area. That's all I did on the next page here. The area function evaluated at 30 is going to be the negative of x squared. That becomes negative 30 squared plus 60 times 30. That's negative 900 plus 1800 for 900. Now, to make sure you answer that in terms of the problem, the area dimensions were measured in feet, so the area has to be in square feet. So this is 900 square feet is the maximum area. Now, if we were drawing this out, the maximum area occurs, like I said on the previous page, when this rectangle is actually a square. All of the sides would be 30, and you know that the area would be 30 times 30, which is also the 900 there. So pretty straightforward problem there. Please do try the homework for this section, especially the word application problems towards the end like this. And remember, I'm not asking you to do any problems I haven't first worked something like myself. I've done the entire book homework assignment, which should model very closely the My Math Lab assignment. So please look there if you need any help. Otherwise, always let me know, and I'll be glad to help out.